Okay, then, so very quickly, just looking at a simply supported beam again. This time with a uniformly distributed load. So that's a load distributed across the whole of the beam, and we will call that small w. The convention that I will use is small w is force per unit length. So the total force on the structure then is big W, capital W, which is equal to small w times L. Okay. In different textbooks you will see typical steel designers' manuals tend to operate with a total W, and then other concrete in particular, for example, will use a small w, which is a UDL in terms of force per unit length. So capital W is a total force, the units of force, which could be kilonewtons, for example. So this could be in kilonewtons per meter, and this would be in kilonewtons, for example. So again, we have reactions at A and B, and again the reaction is provided a horizontal reaction and a vertical reaction at A, and just a vertical reaction at B. But because the load is just vertical, the horizontal reaction is going to be 0 from our sum of forces in the horizontal direction, or the x direction if you like. So we have RA and RB. We won't do this fully mathematically. We're trying to get into the habit of just looking at something and determining by observation or by inspection how things are, and we can see hopefully from that RA is equal to RB, which equals to small w times L divided by 2. So it's half of this total load. Okay, so that is our RA and RB reactions, and then so we can immediately draw the shear force diagram for if this is some value x along the beam. General case, we have this reaction here, which is WL divided by 2, and then we also have coming down some UDL, which is WX. So the weight per unit, or force per unit length, times the length, the distance, and that's acting in the downwards direction. So the shear force at the cut, wherever we take the cut at some point x along the beam, is equal to V, we call it the shear force. So V is equal to WL divided by 2 minus, so we've got WL on 2 going upwards, and then WX. Okay, so if we consider this equation for our shear force, if at A, where x is 0, this term drops out, so we're just left with WL divided by 2. Okay, so if we draw the shear force, then we start at WL on 2, And again, we'll draw it positive in that direction. And then we'll get to some point, and let's take the halfway point. That will vary linearly with x. X is to the power 1, so it's a linear variance. And when we get to the midpoint, which is L upon 2, x is L upon 2, so we get WL upon 2 minus WL upon 2, so it's 0 at the midpoint. Okay. Then as we go beyond the midpoint, this term gets bigger and bigger, again linearly, until we get to the point B at the beam. So this is point B, where x is L, and so we get WL on 2 minus WL, which gives us minus WL on 2. Okay, so we get a shear force of minus WL on 2 down here at that point there. So we get, not drawn that very well at all, that is supposed to be symmetrical. Let's just give me 1 second. So we end up with a shear force where that's B, and this is the midpoint where that shear force comes through, and that's symmetrical WL on 2, 0 through the midpoint, and then WL on 2 minus WL on 2 at the other end. So for the UDL we get a linear shear force, linearly varying shear force, which cuts through 0 at the midpoint. Okay. For the moment, again, if we take a cut at some point x, and we're looking to get this internal moment, the bending moment internally, we end up with WL. So the moments at this cut here are equal to so mz internal, or rather m at the point x is equal to WL on 2, which is this reaction here, multiplied by x, and then minus, and then we say this Wx is a force, and it acts, if we integrate this force, the average distance away from the cut, if you like, is x upon 2. Okay, so minus Wx times x divided by 2. Okay, so again, if we start where x is 0, the moment is equal to, this term has a 0 multiplier in it, and this term has a 0 multiplier in it, so we end up with a moment of 0 at the reaction. So if we draw the beam where this is A and this is B, we end up with a moment of 0 at this point, and if we come to the midpoint where x is L divided by 2, we end up with a moment which is equal to WL divided by 2 times L divided by 2 minus Wx is L divided by 2 times x is L upon 2 divided by 2 is L upon 4. So we get WL on 2, so that's WL squared divided by 4 minus WL squared divided by 8. So a quarter of WL squared minus an eighth of WL squared is 1/8 of WL squared, so we get WL squared divided by 8. So at the midpoint we end up, we'll draw it on the negatives on the sagging side, so this is on the tension side, and we end up with a maximum bending moment at this point of WL squared, small WL squared on 8. Okay. And then because this is a squared term, we can see that that's a parabolic curve, so that this will be a parabolic curve which passes through the maximum WL squared on 8 and then back to 0 at point B, where we have a pin, so it cannot carry any internal moment. And if we plug in for x equals to L, we can, I'll plug it into the formula here, so we get WL on 2 times L this time, minus Wx is L times L divided by 2, so we get WL squared over 2 minus WL squared over 2, which equals 0. So mathematically that comes back to 0 from our formula that we derived. So that is bending moments under a uniformly distributed load, small w, in force per unit length, which gives us a parabolic curve with a maximum value of, let's make that clear, WL squared divided by 8 midspan, and the shear force WL on 2 linearly through 0, WL on 2 minus at the other side. Okay.